All right, hello everyone. Welcome to our next lesson in polynomials. Lesson 10 this time. This one has to deal with something called multiplicity. All right, so in our last two units, lessons, if you will, we looked at the idea of end behavior and discovered like what happens when you have a function and do you have, does it start high, does it start low, end high, end low, and it really dictates what's happening at the ends of a function. So why does a parabola go up forever on both sides, or why does a cubic, sometimes start high, have a couple bends and end low, things like that, right? So we discovered some things like that, but we wonder, what else we can discover on a polynomial. So we also know from our previous work what x-intercepts do. So we can describe where x-intercepts are on a graph. So if we have, so if I have a picture of a graph here, I have a function um, like this, I can describe its end behavior. I can describe here and here, like where it crosses the x-axis. So with that information, and I can even have find a y-intercept usually, um, that paints a pretty clear picture of a function. But there's one thing left that we have not discussed much, and this comes from a problem that was on a little assessment we did recently. Most likely you did it on Edge Elastic. And there was a question where you had a function that had roots. Just I forget the exact example, but let's say it had intercepts at, I believe it was -1 and 9. Okay, something like that, right? And you had to list all the polynomials that had those x-intercepts. And one of them um, was x plus 1 times x minus 9. Does that have those as x-intercepts? Yes, it does. But then another option that was listed is x plus 1 times x minus 9 squared. Does this function have these numbers as x-intercepts? A bunch of people said no, because the squared somehow changes this to a different factor. And so I think a lot of people were thinking that like squaring the minus 9 turns it into like a positive number, like a positive 81 or a positive 9, something like that. And it changes the x-intercepts. But does it? Think about it. If you take 9 and plug this in for x, what's 9 minus 9? 0, right? Same thing you would get here. But the difference is it's squared. What's 0 squared? Still 0. So it is an x-intercept. And that was a little piece of understanding that we get from that. But then the question then becomes, clearly squaring it must affect the graph somehow. So the fact that I have a duplicate copy, essentially, of the x minus 9, well, it does affect the graph. And this lesson, we're going to see how. Okay, so here's a few functions, if you will, a little bit of a warm-up for you. So x minus 3 squared. Now, x minus 3 squared, you might remember, is a parabola, and sure enough, the graph is a parabola. Now, in this particular case, it has an x-intercept of 3, and it certainly does. But when it has an x-intercept of 3, something we hadn't really thought about before is it doesn't pass through the axis at 3. It touches the axis at 3, right there. 3 comma 0. Interesting. Now let's look at the second one. And this really kind of illustrates the point. The second one and also the fourth one. So take a look at this one here. It's got two x-intercepts, -1 and 3. So at -1, what's happening? It passes through, right? So x plus 1 passes through the graph. Perfect. What about x minus 3, right? So if there's an x-intercept at 3, But what's happening? It's squared. When it's squared, in that area around the 3, it's acting like a parabola because of the squared. Now, that's super interesting. Why would that do that? So it doesn't actually pass through the axis. It touches it and bounces off and continues on the same side. Why would it do that? Let's look at a few others. Same thing down here. Here's one with a third power, x minus 3 to the third power. Now, this is interesting because it's acting like a cubic. Well, it is a cubic, right? X to the third. So this is a degree 3. And so it's acting like a degree 3, right? It just happens to pass through 3 rather than 0. And it does this funky S-curve. And what it's doing is it's passing through 3 almost horizontally. So you may wonder, what, are all of these points x-intercepts? The answer to that is no. It's still only passing through the axis at 3. And how could you prove that? Well, pick a number that's close to 3. Let's say we choose a number like 3.01. Let's choose a number that's really close to 3. And let's plug it in. 3.1 minus 3, or 3.01, we're going to get 0.01, and that's to the third power, which is going to be, believe it or not, 0.000001. It's not 0, but it's super, super close to 0. So it turns out the only number that gets you 0 here is 3. So there's only that single x-intercept. But the degree of 3 does make it kind of have this interesting S motion. Let's look at this one. X minus 6. Now, as we predict, x minus 6, x-intercept, passes through the axis. And at x minus 3 squared, it bounces like a parabola. Now, wait a second. Think about this for a second. Now, x minus 3, we had an x minus 3 term up here, right? And x minus 3 squared by itself is a parabola pointing upwards at 3, right? Okay, fine. Same thing here. Parabola at that point. Here, parabola at that point, but it's upside down. Now, this isn't negative, is it? I mean, x minus 3, no? I mean, that's still a positive x. So you can still plug in a number. You can plug in like, you could plug in 3, right? Or 3.01, and you'll get a positive number here. So here's a question I could pose to you. Why is it that despite this not being negative, it still has a curve that comes down? Well, let's think about this. One tool that we can use to think about this is determining end behavior, right? So if you think about end behavior, now this is a cubic, right? And we can tell because it's got an x and an x squared. So this is degree 3. Positive, right? All my x's are positive. And so it's going to have, this shape that we discovered during the last lessons. And it certainly has that shape. So it starts low. So on the left side at the negative infinity, it's going to hurt at negative infinity as well. Okay? So it's going to come up from the bottom. The first number it hits, the first x-intercept it hits is 3. So the problem is it's not going to jump above the axis to make a parabola curve. It's going to make a parabola curve right where it is. So it is going to touch the point and bounce off of it. And that's what the squared seems to be doing here. It is touching the x-intercept and bouncing off of it rather than going through it. But at 6, it does go through it. So is it really just a directional thing? Well, kind of. Now, here's one other thing you can do. Again, you can prove what the difference is, okay? The main idea is, again, the question is, why is that part negative when the one above it is positive? Let's go back to this one. So the reason why this is going to do this is let's look at numbers near 3, right? Again, we're going to choose x value, right? And I'm going to choose numbers nearby 3. I'm going to do, say, 2.9 and 3.1, okay? And we're going to look at y. But I'm not going to fully calculate it out because, again, the value itself doesn't matter. What does matter is the sign, whether the number is negative or positive. So in this particular case, let's say we plug 2.9 in for x. 2.9 plus 1 is it positive or negative? It's 3.9, so it's positive. So you're going to get a positive. Now 2.9 minus 3, now that's negative, right? But it's going to be a negative that's squared. What happens when you square a negative? You get a positive. So positive times positive is positive. Same thing's going to happen with 3.1, right? 3.1, excuse me, plus 1, well, that's positive. And then 3.1 minus 3 is positive, and that's squared. And positive times positive times positive is positive. So that's why both sides here are going to be positive. Part of the reason, again, so a way to think about it is like the 3 comes after the other x-intercept. And so when you plug it into that x, when you plug it into the solitary factor, it's creating a positive number. Compare that to this one down here. So again, the duplicate factors of 3. So let's do the same thing. We're going to have x and we're going to have y. Okay. So in this particular case, we have x is, say, 2.9 and 3.1. Okay. So in this case, if you do 2.9, 2.9 minus 6 is negative times negative squared. Negative times positive equals negative. Same thing here. If you do 3.1, again, you're still subtracting 6. Now it's negative times positive squared. 3.1 minus 3 is 0.1. You square it. That's positive squared. But that's still negative. And the reason why is because the first factor, the one that's solitary, is negative. That's what's causing it to bend down instead of bending up. So here's the big piece of understanding. In a polynomial, if you have a factor that's a solitary linear factor, so an x plus 1, an x minus 6, there's no exponent on it, it's just a solitary x, the function will pass through the point that's listed. So if you see a factor of x plus 1, it will pass through negative 1. Anytime you have a factor that has a square factor, actually generalized to any even factor, if you have an even exponent, it's going to bounce. And so it will touch the point that's listed. So in this case, if you see x minus 3, the x-intercept is 3, it will touch 3 and then bounce off of it and will stay on the side of the axis that it was on before. So whether it goes from positive to positive or negative to negative. And then finally, you won't see this as often, but if you have a triple factor, so x minus 3 to the third power, anytime you have a factor to the third power, it's going to cut through the x-intercept in a horizontal fashion. The official term we use for this in calculus is an inflection point, or a point of inflection. What's actually happening here is the graph is changing from being curved down to being curved up. So I like to think of it now as kind of like an S curve. So it's going to pass through the axis as an S curve. And the reason why it's going to pass through the axis is because a negative cubed is negative and a positive cubed is positive. Okay, so there's your big idea. There's really not much more to this than that. But let's take a look here. So different end behavior. Um, we don't have to worry so much, but multiplicity in particular. Okay, the power to which a factor in the factored form of a polynomial. So for instance, if you have the polynomial x minus 1 squared times x plus 3, the factor x minus 1 has a multiplicity of 2. So multiplicity um, is a fancy way of saying that there's two copies of the x minus 1. And the x plus 3, there's one copy of the x plus 3, because you could put a 1 here. So that has multiplicity 1. So that's the definition of that word. Okay, so now that we know about multiplicity, this allows us to sketch fairly accurate rough graphs from factored form. So here's a function, x plus 9, x plus 3 times x minus 4. So what we're going to do is we're going to sketch a graph, and then we're going to consult Desmos and see how good we are. Okay, so here's x plus 9, x minus plus 3, and x minus 4 squared. Let's write down everything we know about the function. We know its x-intercepts. Oops, menu. Its x-intercepts are -9, -3, and 4. So we know it's going to pass through or touch potentially here, here, and there. Okay. So what else do we know? We don't have a y-axis. I mean, we could figure out the y-intercept. For this function, it's going to be 27. Now that's squared, so you'd actually have to do 27 times 16, which is um, um, that's going to be 112 plus 320. So you're looking at 442 maybe? So don't quote me on that, but it's a big number. And you're going to notice that's why the y-axis is actually not even scaled. When we attempt to sketch a polynomial, we're less concerned um, about the actual values. What we are concerned about is the general shape of it. Because the values we can get by plugging in values for x or finding the y-intercept manually, lots of things. Okay, degree. 4. Why 4? It's got 4 factors. 1, 2, and then it's got a multiplicity of 2. And so it's got a duplicate x minus 4, total of 4 things, so it's a degree 4. All the x's are positive. So what kind of end behavior will it have? So it's going to have, as x approaches negative infinity and x approaches positive infinity, on both sides, even, it's going to be like a parabola. Y approaches infinity. So what's going to happen? It's going to start high, and it's also going to end high. So it's going to do something like this. It's going to come down, and the first thing it's going to do is it's going to pass through the first x-intercept. It's going to pass, because that's a linear one. It's going to pass, but x minus 4 is squared, so it's going to bounce. Pass, pass, bounce. So it's going to come down, pass through that, pass through that. But then it has to turn around because now we're on the positive side. So we can't cross the axis again to bounce off of 4. We have to bounce off of it right where it is. So it's just going to come straight back down and bounce off of 4. Okay, so let's take a look at the actual graph itself. So I'm going to see if I can do this here. Do this, and here we go. Recording. You can see my lovely computer screen. Here's my Desmos graphing calculator. X minus 9. Oops, not 90. Whoa, okay. X minus 9. X. Oh, it's plus 9. Sorry. It was X. Caps lock is on. It was X minus 1. X plus 4. Oh, X minus 4 squared. Oops. Wrong sign. So we had a plus, and that was a plus. So it was, let me take a look here at the function again. It was, yeah, x plus 9. Oh, x plus 3 and x minus 4. Okay. All right, does that look like what we had? Well, no clue. And if we try zooming out, we realize we're going to end up in kind of a big mess here. So let's go and change our viewing window. X-axis. Let's do the one that was on the board, negative 10 to 10. Oh, that's looking a little bit better already. And then we'll do negative 1,000 to 1,000. Perfect. Look at that. Okay. 432. I was almost there. I said 442. Okay. So let's take a look at this function. Hey, look at that. Now, how well do we match? I think we did a pretty good job there. I forgot the arrow on that part. Um, but that is not too bad at all. Okay. I think as long as we keep following those same steps, we could draw just about anything, right? And again, scale comes after the fact. We can always look at the actual y values at another point, right? Okay, let's try one or two more just to make sure we've got it okay. Um, okay, all right. So sitting near, okay, so here's a little activity that we could do in class, but again, we'll just kind of do it together, right? And let's pick a few of these that we do, all right? And you can check your sketch using graphing technology. But hopefully we won't need to do that. Again, y-axis is no scale on here, so we don't really care too much about how much it bends, just where it passes, right? Okay, so first one, x plus 2, x minus 2, and x minus 8. So again, think about what the x-intercepts are. Negative 2, 2, and 8. Any multiplicities? No, so it's going to go pass through all three of those points. Okay, cubic, right? It's a cubic function, so it's going to be odd. So it's an x to the odd and positive, so it's going to start low and end high. Okay, so that means it's going to start low like here. It's going to go pass, 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 like that. And there you go. You've got yourself a nice little function. And let's go ahead and check it just to be safe. And we'll show you that that's pretty much exactly what it should be. X plus 2. Oops, wow. Didn't mean to do that. Uh, X plus 2. Caps lock key keeps coming on again. X plus 2. X minus 2. X minus 8. And there you go. Now this graph is a little bit wider than you expect because of the change in window, but you get the right idea. Okay, let's try a few other ones. Let's erase this. Okay, we'll erase our work here. And let's try one with a 2 in it. See what happens. Erase. Okay, so let's try B, right? Negative x plus 2, x minus 2 squared. Okay, so what's going on with this one? It's got two x-intercepts. It's got one at -2 and +2. Now this one here is squared, so this one's going to be a bounce. Anything else you notice in this one? It's negative. Okay, so what's the degree of this one? It's got an x, it's got an x squared term, but it starts with a negative, so it's a degree 3. But the negative means it's going to open in the opposite direction from the last one that we did. It's going to start high and end low. Remember, an easy way to think about it with the the odd degrees is it follows in a similar direction to what you'd expect, like the slope of a line to do, just with a few more curves to it. Okay, so it's going to have an x plus 2, so it's going to have a -2, it's going to have a +2, but it's going to bounce off +2. So it's going to come down through this. It's going to come back up to 2, bounce, and back down again. I kind of missed a little bit on the graph there. But the lovely part is um, I could shift a little bit, but you get the idea, right? It's going to come back here. Maybe I can fix this part a little bit here. There we go. Perfect. So it's going to look like that. And yeah, go ahead and check it. And you'll find that that's in fact true. Okay. Let's do one more here. Ooh, let's do F. F is a good one. It kind of covers everything. It's got a few things that are happening here. Okay. So I'll erase all this. So let's look at this one. X to the third, x plus 4, x minus 3 squared. Okay. What are the x-intercepts? -4, 3, and also 0, because 0 times anything is 0. Okay. What degree is it? X to the third, another x, two more x's. It's a degree 6. Any negatives? Nope. So it's a degree 6. It's a degree 6 positive. So how is the function going to open? It's going to do this. It's going to look like a parabola, but it's going to have a few more pieces to it because it's a degree 6. So there'll be quite a few twists and turns here. Okay, so let's talk about the x-intercepts. X plus 4. Multiplicity of 1. This is a linear factor. Because it's a linear factor, it's going to pass through the axis. We'll do a pass. X minus 3 squared, this is going to be a bounce. It's going to bounce off of 3. So it's either going to bounce like this, or it's going to bounce like that. Okay. And then finally, this here, this x to the third, remember what an x to the third does. So the third has an S-curve. And so it's going to curve through the x-intercept of 0. Okay, so here's how it works. So we're going to start high, right? And the first thing to do is we're going to pass through the first x-intercept. Okay, but now it's going to come back up again. But because it's going to curve through 0, kind of like that. Kind of, I know this one is a little tricky to do because my pen only has so much. My pen only has so much. There we go, kind of like that. So it's going to do this S curve through that. Now, here's the next thing. It's got to bounce off of -3, or the x-intercept of 3. So it has to come back down and bounce off of 3 and before continuing back up again. So you're going to have a function that's got kind of a funky little wave to it. Let's see what that looks like on a graph. So let's change this up. X to the third. X plus 4. X minus 3 squared. Okay, and I'm going to shorten this up a bit. So let's say, because we don't need all this x-axis all over again, but let's just go to 1,000. So what do we do? A y value of, let's do 500. Let's say, or we'll do negative 1,100, and then we'll do this to be 500. Okay. Okay, so you can kind of see what's happening here. Um, and to really illustrate the point, I could even like shorten this up a little bit, maybe shorten the x, but it doesn't even matter. It goes down and then comes up again, as we pictured. Here it's going to go down, but it's just going to dip really far down. We didn't know. And then it's going to do an S curve through 0. And that's what it's trying to do here. And you can kind of see it. Here it's kind of wider than mine is, but just because of the scale that I used. So you can see how I kind of S curved it. But it's not going to be on that S curve for long because it has to quickly come back down again to pass through 3 and to bounce off of it. And sure enough, if you follow all of that, you get the correct end behavior. So one of the lovely parts is the end behavior kind of goes along with these functions. If you have the correct curve and pass and bounce, your graph is going to point in the correct direction. So it's almost like the two almost check each other. Okay, so finally, um, as usual, as I did with the last one, it helps to be able to do your end behavior statements for this. Now, you could write it out in words, but I tend to prefer to use the notation. So x approaches negative infinity, y approaches infinity, because that's the side, and as x approaches positive infinity, y approaches positive infinity as well. Okay, and there you have it. That's how multiplicity works. Now we've connected end behavior and x-intercepts and multiplicity, and we have a complete picture of a function. And all these other functions will work much the same way. Just think about whether they pass through the point or bounce off the point. Make sure you work in your end behavior because the end behavior will be kind of like your error check to make sure that you got all the correct passes and bounces. If you do, then the function will point in the correct direction that it should. All right. So there you go. Hope you have a lovely time with this, and I'll see you next time.